So we really cover these blind zones, which were called blind zones. What is happening here? We know from the similar latitude in South America and other parts of the world, there's phenomena that occurs there during geomagnetic storms. But over Africa, what is happening? And the unfortunate part is the instrument that I use for most of my research, it perfectly covers South America, which is the GOLD instrument. GOLD is a far ultraviolet spectrograph that was launched in 2018 by NASA. They actually put it on a commercial satellite, so that was really neat what they did in the SC-14. And so that instrument, it actually has a field of view. It's in geostationary orbit, and it has a field of view where it actually covers the entire South America, which really helped me in my research. Unfortunately, it only covers part of the blind zone that we want to cover. Parts of East Africa, they are not really covered by gold, unfortunately. So that could also be one of the solutions that could have helped us. So which is why you need CONGA, even more reason for us to need CONGA, because the other options that we have, alternatives, they still don't cover that area that we're interested in. So that's why it's so important. And so back to my work now. So the work that I did, I'm going to present most of the doctorate work that I did, was to try and use a multi-scale approach. By multi-scale, meaning we're trying to use different instruments to detect irregularities at different scale sizes, because each of those instruments that we have, be it the satellites that you see on the right-hand side here, where you have gold in geostationary orbits, or the SWAM satellite, um, Elguvi, these instruments all have a different scale size or resolution when they're detecting irregularities in space. Of course, the main instrument that we used was GNSS. Here's a map of the ground-based instrument that we used. We have the GNSS or GPS receivers to all frequency here. I also have magnetometers that we have in low latitude. These magnetometers were used to calculate to infer the equinox drift from the equatorial electrojet. We also had a digisonde layer close to the equator. If you can see here, this is the magnetic equator here, the deep latitude, to try and detect, to look at the F layer frequency at the bottom side of the equator. So this is basically just a rundown of the instrument that we use. We also used an Oscar imager as well, which you can see in pink here, which is more of low latitude near equatorial station, to detect these irregularities. And so all of these, when we take all of these angles from different views from different instruments, we'll be able to see more information about the structure of the irregularities. And so this is some of the things that we could do with CONGA once we get the instruments installed. We already have the science, already have the techniques, and the code to do that, to come up with the maps and the calculations. So it's just a matter of, once we get a CONGA deployed, we'll now be able to to perform this kind of research once we have the GNSS receivers installed. And so I also used a multi-index approach, which was basically derived multiple ionospheric indices from the total electron content. The GNSS TEC, I used the GOPI software to actually come up with that GNSS TEC. And then from that, derived the percentage deviation in TEC, TEC, which is the difference from the average 5 most quiet days of the month. The reason why we took the average of the 5 most quiet days of the month is that sometimes the diurnal variation of TEC, you also have diurnal variation in TEC as well. And so we also wanted to take that into account as well in the calculation. And we also, to detect irregularities, use the ROT, or the rate of change of TEC. So the rate of change of TEC gives you the large phase fluctuations in TEC. It gives you the large scale structures. But then one of the key indices that we came up with is the ROTI, which we calculated actually, is ROTI, which is determined from the ROT, which is basically the derived from the ROT as well. So the ROTI actually gives us small scale irregularities. Of course, it's a range. but it gives up to kilometer scale irregularities. I remember the irregularity structure. Um, you have the cascading effect when plasma bubbles are formed, they fragment into smaller irregularities. So this is also why one of the reasons why the multi-scale approach is important, because you have the large scale bubbles, which you can see with an imager, but you also have the smaller irregularities, which you can detect using ROTI. And so for this calculation, you used 10-minute ROTI. So the way to classify intensity of the irregularities is this is how intensity calculate the intensity. So anything greater than 0.2 ROTI is considered strong. Uh, Another thing that also used instrument is the scintillation monitor. It's the high frequency which we can calculate from the high frequency GNSS receivers. And that can also give us the S4 index as well from those kind of receivers. Uh, and that S4 greater than 0.7 is considered strong. So of course, these scintillation monitors, we have them in South America, but they are a bit fewer. So they are very good because the scintillation actually gives you the direct effect on, cycle slips on the L1 and L2 band. So they are quite important and useful. Unfortunately, they are more expensive. uh, Hopefully we might get one or two, perhaps more closer to the equator uh, over Africa, but they're a bit more expensive than GNSS receivers. So the idea is to try and use ROTI, try and create a correlation between ROTI, which is from the GNSS receiver, and the S4 index, so that because we have these GNSS receivers in more abundance, it will allow us to be able to infer what is happening in the scintillation. So that was basically the idea. And so from that total electron content, one of the things that I mentioned is the structure of the irregularity, where you have the plasma bubble having the side walls of the bubbles and the inside of the bubbles. And so here I have a map here, a diagram here showing us the structure of an ionospheric irregularity, where you have total electron content that is inferred uh, when a plasma bubble was detected. And you can see that, you have these depletions uh, inside the bubble. So on the right hand side now you have the TEC gradient now, which is inferred from that same total electron content from that pass of the plasma bubble. And you can see that there are, sharp gradients at the edges. So that's the edge of the plasma bubble where you have the larger gradient between the background and, the bubble itself. And then you have smaller intensity irregularities, which are more long lasting on the inside. And so all of these are different scales in size, and they can be detected by different instruments. So to calculate these gradients in TEC, uh, I used the time step method. I have a map here on the left-hand side showing you different methods. You have the station pair method, the mixed pair method, and the time step method. Um, of course, all of these have got their advantages and disadvantages, but I'll just focus on the time step method. Why? So the way it works is, we take uh, a satellite, and receiver pair. So it's just one satellite and one receiver. And then you calculate the difference in TC, or the gradient in TC, between the point T1 and T2. And that gives us the gradient of the TC, and that divided then by the distance traveled by the IPP. I remember when you are calculating the TC, we are projecting it to a certain point um, in the thin shell model of the ionosphere, which is about 150 kilometers at that IPP. So the distance that is covered by the IPP, which is this one, we then divide it by the difference in TC to get the gradient in TC, which is more preferable to the mixed pair method, because in the mixed pair method you're using multiple satellites and receivers at the same time, and so you have ambiguity, you have a lot more biases and errors coming from that, from those two as well. And of course, one key assumption of this method, which makes it work, is that you assume that the distance traveled by the IPP, within that time that it travels that distance, the irregularities, let's say there's an irregularity within that space or above that IPP, we are assuming that the irregularity is frozen in space, so that the rate of propagation of that IPP is much, much faster than evolution of plasma bubbles, which we know is the case as well. And so from that, from those gradients or GNSS receivers, we're able to get ROTI. We're also able to get the S4 index from the high frequency GNSS receiver. So what I have here is I wanted to show the climatology of ROTI, which we want to use as a way of as a proxy for the S4 index. On the left hand side, they have a couple of stations in Brazil. On the right hand side, we have the S4 index for the similar stations as well in Brazil. And this is showing us the climatology during the year 2018. I also added here at the bottom the symmetric H index at the bottom here. So what we see from this graphic is that we have the expected climatology where it's higher, during the in this period where you have the local summer, and of course in the local winter the intensity of the irregularities is lower. But what I want to draw attention to is at the symmetric edge we have these this is the minimum symmetric edge. You have these peaks in the bottom here, which are indicating a storm occurrence. And in many of the cases, for example, in here, this was May, we see that the symmetric edge, which is showing us storm occurrence, it seems to coincide with the S4 index as well. In a couple of cases, actually, not just in May, but also in September. So, in one of the case studies that I'll present, I'll also show how in the month of October, we saw an enhancement of irregularities during storms as well. And just to show the coherence here, I'm just showing the time of maximum ROTI as well, just to show when the irregularities are most intense. So we find out that over Brazil, the ROTI or irregularities are most intense between 8 and 3 a.m., 8 p.m. and 3 a.m. Local time. And the reason why we took maximum ROTI here was sometimes when you average the ROTI, you actually end up having a lower value. So that's why I took the maximum to see when it is most maximum. So we see that generally the ROTI has got a good correlation with S4 index. So these are one of the things that we can do to try and calibrate the ROTI that we'll get from the CONGA receivers. And maybe if we can get a scintillation monitors near those places that we can use to calibrate them so that we can have more, an inference of ROTI and the S4. And so, like I said, I saw some correlation. We saw some correlation between storms and irregularities. And so this is one of the examples that we have. This is from October 2018. We have a storm that occurred from, of course, here I'm showing the quantities here, geospace quantities from the 5th of October to the 13th of October. So the storm itself actually occurred on the 7th, but we just showed the variation as well a few days before the storm, uh, as well as after the recovery phase. So this is the same methodology that will follow to try and see what was the variation in geospace before the storm and how did that affect irregularity development compared to during the storm main phase and then the recovery phase. So one feature of the storm, you can see that it has a really long recovery phase. It had a really long recovery phase. Of course, the symmetric edge had multiple negative incursions as well. We had highly oscillatory BZ even during the recovery phase, and that also has got impact on irregularities because now you have effect of prompt penetration electric fields and so on and so forth. And so this kind of storm is considered moderate, symmetric H minimum around minus 60 nanotesla, 60 nanotesla, yes. And so that would be considered a moderate storm, which we would not normally expect to have a great impact compared to intense storm, but we will show that the effects were significant. And so here I have the response of the post-sunset ionosphere to that storm. Again, I have here a plot of the gold, 135.6 nanometer radiance. This is over South America, in the same area that we have the GNSS receivers. I also have a couple of receivers in Brazil as well. This is close to the ionization anomaly from the north all the way to the south. And then you have some equatorial station in the middle. So these are GNSS receivers where we got the ROTI. But we also have the spatial gradients in TEC in the same stations as well that we have as well. And so what we observe here is that from the 5th, which is a quiet day before the storm, the 6th of October, which is this day here, we know that there was no storm here. So we see that we have quite an intense and well-defined ionization anomaly. But what we see is that the ionization anomaly on the 7th of October, which is the day of the storm, we have a weakening of the ionization anomaly on the 7th of October. And that also coincides with suppression of irregularities because see that intensity of ROTI is higher before, so is the intensity of the ionization anomaly. But then during the main phase of that storm, uh, we have a weakening that is also seen in the ionization anomaly as well. And then, of course, as the storm progressed, you see that you have then an intensification of the irregularities that is in the recovery phase. That was coinciding with that oscillation in BZ. So that could be because of prompt penetration electric field, where you have a really sharp ROTI as well, peaks in ROTI. And then also you can see that on the 9th of October, that same night as well, you see that you have a recovery in the ionization anomaly as well. You can see the crest as well. Um, and then after that, you have again some suppression as well. So you have that cycle where the irregularities, they're not really showing on the equatorial ionization anomaly area, but you can still see them closer towards the equator. So that could show that, irregularities, they didn't really propagate that effect where they flow to low latitudes. They didn't really happen uh, as much as before. They didn't actually reach low latitudes. Again, here on the bottom, it's just showing the same thing, but of course in a different scale. We are seeing the all-sky imager, which is located in San Luis, which is close to the equator. And what we see is that we actually have plasma bubbles as well. Uh, yeah, unfortunately, we didn't have data on some of the days, but on the 5th, which is the day before the storm, or on the 6th of October here, you see plasma bubbles. And of course, the structure that we see from a no-sky imager is not exactly the same as what you see from ROTI, because of course the field of view of this Oscar imager is smaller as well. And also you are looking from the bottom, looking up. Of course, both of them are actually imagers in a way, the gold imager, but the 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 scale size that we are seeing of plasma bubbles here and there is not the same. So that actually helps us to see that the structure of plasma bubbles is different based on the instrument that you are using, and you can have more detail the more instruments you have. So which is why CONGA is also important, because we need as many instruments as possible to get that. And then on the right hand side is just showing the plasma gradients. These are the gradients in TEC. Again, just like there's a difference between the two, you can see that they are showing the same similar effect, showing you ROTI, showing you plasma bubbles, but the gradients are really showing you not. So the ROTI is showing you the intensity of the irregularities, but the gradients are showing us the variation of the temporal variation of the irregularities, where you can actually see the structure here as well, following the same pattern, where you have peaks here on the 9th and suppression on the main phase of the storm, likely due to a counter electrojet. Uh, but what we see here is that these are gradients in TEC, and you can see that there's sharp peaks at some edges, and then you have in the middle of them, amplitude decreases, and then you also have sharp peaks. So these peaks are actually correlated to the structure of a bubble, which I'm showing here at the bottom, where we have an image of a plasma bubble, and we took a slice of the intensity from the Oscar imager, which is like a profile along this line, and you see the variation. So that variation is showing you that you have these uh, gradients, sharp gradients at the edges, just like I showed in the earlier from Pradipta. And then you have the depletion in the bubble. So each depletion is actually showing you like these two bubbles here that you have. You have the depletion from each bubble, but then you see that you have sharper gradients at the edges. And so these are the edges that you're seeing here in the gradients in TC. So these gradients actually can influence and affect GBus networks. Uh, so those kind of networks can be affected when you have ground-based augmentation systems and you're trying to transmit even correction signals uh, above that station. When you have these gradients, then you can also have errors. So that's why it's so important for us to study these. And so you see a correlation between not only the structure of the bubble, but also how the gradients relate as detected by either using an OSCAR imager or by using GNSS receivers. And uh, so this is there was a lot of interaction between the plasma density and irregularities here. I'm showing a map now of the ROTI, and then this is a map of a snapshot of the gradients, spatial gradients in TEC for multiple stations, which are calculated over Brazil. And then on the right hand side, unfortunately, it's not really clear to see, but I'll zoom it out in the next slide. You are seeing the gradients in TEC, but this time separated by the PRNs. And so for each of the PRNs, we have the variation in the gradients. In the previous one, it was all of the PRNs combined together. So what we saw is that if you remember, on the 9th of October, that's the day when we had the peaks in irregularities. That day we had the most enhancement in TEC, and coincidentally, we see that the intensity of the ROTI as well was also maximum on this day that we had the increase in TEC. And of course, that is expected because for you to have irregularities, you also need to have a higher background TEC so that you can have sharper gradients. So the same thing also is seen in the map of the gradients in TEC, which is a snapshot of the gradients in TEC. That is 2230 to 2359 local time. This is showing now the gradients in TEC, and you see that they also have the same similar variation in terms of coverage and intensity as well compared to the ROTI. So you see that there is indeed a relation between the plasma density and the irregularities. And this, on the right-hand side, you see that not all the PRNs are showing that those gradients are detecting those gradients. So that also shows us that we can use this in GNSS applications, correction of positioning systems, because for each PRN, we know the position, the latitude, and the longitude. So we can actually detect the direction of the plasma bubble. We can detect the direction where the gradients are coming from. So because we see that this is one station, but not all of them are detecting it. So it's basically we can track the direction of the irregularity, where it is coming from as well. So this is just what I just showed. This is on the left is the same figure you saw with gradients, but this time it's showing ROTI. So again, you see, for example, for PRN number 14, you have this variation that is showing you the GNSS receiver tracking the satellite as it is passing above. That's giving you the structure of the bubble passing or irregularity passing above the station in that instant. ROTI, of course, is showing you the size of the irregularity, but it's not really showing you the intensity, or it's not showing you the variation or the gradients within the bubble. So this is why gradients are quite useful as well, because they give you the structure and the evolution of the irregularity, whereas this one just gives you the intensity as well. And so another case study which we did, which I also wanted to share, is now a more shorter duration storm. If you look at the geospace parameters, you see that they're more or less similar in magnitude to the previous storm that we had. This was a week after that storm that I presented the previous one. Symmetric H is around -50, so this storm is considered uh, minor, and you also have a smooth recovery as opposed to like the last storm that we have. These red lines are showing us the main phase, which was between 14 and 20, 14 and 19 UT on the 18th of October as well. So I wanted to see what is the effect of a minor storm that is occurring. And so here we computed the variation in total electron content, and this is actually the delta TEC, which is subtracting the quiet time TEC from the storm time TEC as well. So I have the maps here starting from the main phase, and then this is where the recovery phase started. And of course, we see that we have a positive storm, about 30 TEC units in magnitude, showing the intensification of TEC during the main phase, but also which continued during the recovery phase. Here we also have the O over N2 ratio detected, and that is actually showing us the evolution in zone of O over N2 ratio. But this one is starting from 2045, from about quarter to 9. This is UT. This is much later around this time here. And that is also showing an intensification as well uh, in the O over N2 ratio on a disturbed day, which was on the 13th, compared to on the quiet day before the storm. So we see that the increase in TEC was also connected to composition changes as well. And so that was during the day and in the recovery phase. But then what about in the night time or post sunset? We know that gold it provides measurements starting from 8 p.m. That is to around 1 p.m., 1 a.m. That is the magnetic local time of that position where it is above the set, so the center where the God's instrument is. That is the local time of that area. So that is the time period that we can have observations. Unfortunately, we cannot have observations during the day. And we were seeing that on the 13th of October, where we have this intensification in the plasma density in the post-sunset sector. We also see very well-defined structures, periodic structures, plasma bubbles, uh, with this very regular separation between them that is over South America that lasted all the way up to 2340 and so PM. And so this is actually showing us these are very interesting structures where bubbles, the structure is preserved and you have that irregular spacing in between them. That is in that particular day. And then also we have a swarm pass where we just took a slice of the pass, which is more or less around 10, 40 degrees longitude, and is showing us this variation of swarm. You can see that there's a lot of perturbation in the electron density detected by swarm. So this is showing you the structure of irregularities, which you remember, if you looked at the gradients in TEC as well, we saw a similar variation. But of course, again, now you have a difference because swarm is now a satellite that is in orbit, and also the scale size that you're seeing is not the same as you're seeing the same effect as the on the GNSS, but now it's on a different scale size. So that is quite interesting to see that we can detect the smaller irregularities which are within the plasma bubble. Here we can see the large scale plasma bubble, but when we slice it, when we take the profile of the electron density, we can see those that are inside, and these are actually the ones that have effect on GNSS receivers. And then on the right hand side, just a comparison of, again, a snapshot at 2355 UT that is showing us the plasma bubble, where you have the ionization anomaly, of course, uh, more or less defined on the eastern western sector. And then you have these irregular periodic plasma bubbles, which are unique structures that we observed. On the right-hand side, we have the total electron content. Again, what you see is, interestingly, a similar structure of the plasma bubble with the same periodic spacing. Of course, you can see that there's some differences, because the good thing about gold is gold can give you this view over the oceans uh, beyond the continent where you don't have receivers, whereas here you don't have receivers here. So gold can give you the full picture. It can show you the full picture of the irregularities. Whereas GNSS, of course, we have higher intensity, we have higher resolution of receivers in the TEC, but we don't really have a large field of view. So you now have a complementary, where you have a complementing gold with GNSS receivers. And also another effect that is different is, you remember this is in geostationary orbit, is looking from top down, where the 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 the, the instrument actually does a sweep, does a scan over the continent, whereas here you actually have instantaneous detection from GNSS receivers. So this is why you have similar structure in general, but you have some other kind of smaller irregularities that you are seeing here that you're not seeing that you're seeing in the TEC that we don't see in the gold. So they have a good agreement, but gold has got a larger coverage, and TEC has got a better resolution.
So
And so
we have
go
5 minutes. Yeah.
5 minutes. Okay, so thank you. Yeah, I'm just wrapping up here. And so these are the irregularities. Remember, we detected these irregularities again. This is the map for the same interval that we showed here in the map for gold. But now we are seeing the same irregularities in ROTI. So now ROTI is giving you small scale irregularities. Gold gives us around maybe 95 kilometer scale size in terms of the plasma bubble, the resolution. But then here you're now seeing kilometer scale size. Of course, again, we see the intensification in the plasma irregularities. Again, you see the same periodic separation, interestingly, even in the ROTI as well, not just in the large scale bubble, but also in the small scale plasma bubbles as well. Uh, the region where you have irregularities is more or less the same, but then you see that you have more resolution here because now you're detecting the smaller irregularities, whereas compared to in the Oscar imager or gold, you're seeing the large scale irregularities as well. And though we see also so gradients, large gradients, long lasting gradients again associated with that, showing, detecting um, uh, these the same bubble, but in a different scale. And so the seeding mechanism which led to the plasma bubbles, we believe was, uh, propagating traveling ionospheric disturbances, TIDs, which we detected also in the TEC and also which we detected in the F-layer flare through height. So we believe that the seeding process of the plasma bubbles was indeed gravity waves as well. And so just to summarize, just looking at the flare dynamics, during the main phase of the storm, there was an intensification in the delta H, which is the electron jet, which we get from the magnetometers. It's showing us just the delta H, the E cross B drift. Of course, we have the other parameters, which we will not get into because of time. Uh, and then in the interval of the recovery phase, where do you have oscillation in ionospheric BC, we had a suppression actually in the delta H as well. And looking at the F layer visual height, we also see that there was a peak close to sunset on that day, which we believe is the reason why we had those intense plasma bubbles as well. And so in conclusion, I used a multi-parameter, multi-instrument approach to see irregularities at various scale. We saw that during weak storms, there was a lot of dynamics that were occurring during the storm that actually are very significant, that can help us to understand the ionosphere at solar minimum. We also saw high variability in the ionosphere using gold as well over regions that are remote, over oceans where we don't really have instruments. We also detected the same irregularities that were found by gold in one instance in a case study. We've also detected the ROTI for the first time. And they also showed the same periodic separation between them as well. And also, they also showed that there's a qualitative positive correlation between the intensity of irregularities and the spatial gradients, but also the total electron content enhancement as well. And so, of course, I will not go into the other aspects, but I believe those are the most important ones. So I believe that, all of this information, we got it from GNSS receivers. And so with the installation of CONGA receivers, hopefully over Zimbabwe, that can also reveal more information because remember, Zimbabwe is in mid-latitude. So there are other instruments that we can install there, perhaps like a fabric pair that can also show more about what is happening in the ionosphere over Africa. So that is something that is very interesting that we can do. With that, thank you so much for your attention.
Oh, wow. Thank you. Thank you very much, Dr.
Yeah,
Garandi.
yeah,
I'm so grateful for taking time to give us this interesting talk today. And I remember you have told me this last year, and I said, okay, hold on, we have so many speakers lined up, but yeah, so it was time for us to have you finally. So
Yeah.
I'm so grateful that you have this presentation, and thank you for this wonderful presentation. Um, I think I enjoyed the part mostly where you mentioned CONGA and you emphasize um, you lay out the need for CONGA to take effect. And that will help our scientific results in a very special way, according
Yes.
to what is seen in your results. And also your results also show that deep minimum activity cannot be overlooked, right? You have shown that using multiple parameters and multiple instruments. So I think you have some questions in this chat box. Let's see.
Okay. Yes, I can see some of the questions.
If you want to ask the question to Frank, you can please do so. You can unmute and ask your question. We have very few minutes left, but we can go over time. No problem. 10 to 15 minutes is always good for us on this program to go over time. So let me see. Who has questions? Oh, there are a lot of questions here. Okay.
Oh, yes.
Mhm.
Yeah.
I think Bruno, do you want to unmute? You are not new on this program, so unmute yourself and ask your question.
Yes, thank you, Dr. Jonah, and thank
Mhm.
you, Dr. Frank. Yeah, I am trying to look at storms within the solar cycle 25,
Yes. Mm-hmm.
and from I'm coming from a surveying background.
Okay.
So on trying to look at them, I was trying to use the DST index. So I wanted to know, you spoke about the recovery time. I wanted to know, when do I say that these are the days for the recovery? Is there a
Oh, okay.
range I can consider that I can
Okay.
also try to put in my work for that purpose? Thank you.
Okay. So your question, if I understood you correctly, how do I close this? If I understood you correctly, is to identifying the recovery phase, right? Or
Yes,
is it?
yes, yes, yes.
Yes. So if you look at the symmetric edge, or you could use the DST, these are similar. The symmetric edge is just it's got a higher resolution. But generally, in the storm time, you see that the symmetric edge before it will be more or less around zero, and then it starts going southwards, becomes negative. When it starts going positive, that's when that is the marker for the recovery phase, up to the point where it returns to more or less zero. That is more or less around. It's not really fixed. You can't really say it's definitive, but in general, from my understanding, that is how you can, identify the recovery phase. Um, and then for identifying quiet days during, I think there's something that you mentioned about quiet days. You can get the most quiet days from Postdem. It's a website which I can share. And I believe they use the KP index to identify the 5 most quietest days of the month. So you can know which ones were the quiet days and which ones were disturbed. Of course, there's different criteria that you can use, but those are generally the ones that I used in my study. I don't know if I answered you correctly.
So I think we have another comment here. I think somebody wants to know how you get your Rhines files. I think Jonathan Jones. You might want to reach out to Jonathan Jones on this email. He put his email here if you have any
Okay,
um,
okay.
yeah,
I'll drop it.
answers to that. So we also have questions from Fraz Bashir. How often the coincidence of gold and GNSS is seen?
That's
Uh,
a great question. Yeah, I think that's a great question. So that would depend on the intensity of the plasma bubble and the latitude. But I did see it for a lot of cases. But there are some cases where the bubble, you cannot see it in gold, but you can see it in the GNSS because maybe the bubble didn't really develop, the cross-beam drift or not so high that it develops to low latitude where the gold can detect it. So it's still the same plasma bubble, but now you're seeing it at different scales. So for that to coincide, the size of the bubble also has to extend to low latitude so you can see it clearly in gold. But the fact that you don't see plasma bubble in gold doesn't mean that it's not there. Sometimes it's there. You can see it in other instruments like Oscar Imager or in the ROTI or in the GNSS TEC as well. So that's one thing that I observed in the study.
Yeah, I think there's need to be more analysis to actually answer the question accurately to understand when and if there is great consistencies there. When you see bubble and then in GNSS and then you check on gold, you see it. I think we need more data to to be able to give you a solid answer to that. And then we have another question. We have Jelitao from Ethiopia. He wants to know how gravity waves are detected and what parameter did you use to confirm its presence or their presence.
Oh, yes. Yeah, maybe unfortunately because of time, I think I was rushing through that section. But yeah, thank you for that question. So for detection of, oh, sorry. For the detection of gravity waves, there are a couple of methods that we can use. In this particular case, we actually were able to detect gravity waves in two instruments. First of all, on the right-hand side, we have detrended TEC. So that was detrended TEC from the maps that you have here. And we took the sector minus 45 to minus 35 degrees longitude. That's the sector as well that we took the profile. And when we detrended, when you do the detrending analysis in that particular area, when you take do the detrending, be it Savitsky-Golay filters, some use bandpass filters. In this particular case, we use a bandpass filter. We can actually see that you have these intense structures which are showing you the peaks of the gravity waves where you have, and then you also have the troughs as well. So you can actually see that you have gravity waves being detected in the total electron content. But then you also have here on the left-hand side, this is the F-layer true height. I mean, maybe it's not so clear, but this is the detrended F-layer true height. And that is actually showing you, again, some undulating, some structures, some wave structures in the F-layer. And so that is how you can see that propagation of gravity waves when you have that shift in the peaks from, was all of these layers are at different altitudes. So when you have that, wave structure and you see that shift, that shows you that this is a structure that is propagating upwards in the ionosphere. And so you also detected it using the F layer from the ionosonde and also from the GNSS receivers.
Okay, so thank you for that. And also I think you can grab Dr. Frank paper or article for this talk he made. At some point, he can also send that to you. And if you want more information about, I think we have a lot of paper that shows you how you can detect gravity waves from GNSS receiver, and we can send that to you as well. Dr. Frank can gather some papers to send to you if you put your email in the chat box. And we also have Valence. Valence. Oh, before Valence, we have another question from Dr. Brafras. Brafras, do you want to ask? To be clear, you want to unmute to ask a question?
Sorry, first of all, thank you for a very nice presentation. Sorry, I joined late, and so I don't have a background for the presentation in the beginning, but it's a great talk, and I'm learning a lot from it. So my question actually specifically is about the dimensions of AI-driven extensions. So for example, how do you see the current scenario of your research, that how you can enable the AI-driven or ML-driven extensions for that, specifically for decision sports, right? So early warning system and I understand that you have using this African part of it, but do you think that the same thing can be done for North America or Europe as well, or in general, like globally? Sorry, my throat is not better, so sorry if you are unable to understand that.
That's a great question. Yeah, so one of the things that we're trying to do is to extend this work because this was mostly observational in nature. But the way that I see it, of course, maybe I will not be able to answer the entirety of your question. But the way I can see the use of AI-driven extensions is in the automatic detection mostly that I see, automatic detection of the irregularities. Of course, the only challenge that you might need is you need the training data to be able to train those systems as well. But there is a strong, argument for the use of AI, especially in developing the tools as well for automatic detection. For example, you saw that the structure of the gradients in TEC has got a certain pattern. So from that, we can actually train models to be able to say, okay, when you recognize this pattern, this means that we have plasma irregularities. We can then set this threshold to say, okay, if it exceeds this threshold, then that means it's it's an intense bubble, it's something to be of concern. Another use of AI that I'm seeing right now is uh, in the reduction of ionograms. Remember, we showed the F layer height. There's so many information that you can get from the ionoson. But to reduce those images, to process the ionograms, is quite taxing undertaking. So machine learning and AI, you can use that to train models that will look at the ionogram data and be able to detect when you have spread F, detect when you have, plasma bubbles, and so on and so forth. And that is my own point of view in particular in relation to my work, but I know there's a lot more that can be answered in that question, which I didn't really, maybe I'll leave to Dr. Jonah
Yeah,
to
yeah,
respond to.
I think you are right. The anomaly detection will be very, I mean, AI will be very useful with the anomaly detection when it comes to irregularities like this. And a lot of people are working on that currently. I think over Europe, we have so many AI analysis or model that are working to understand or to give us a forecast or prediction of irregularities like plasma bubbles, scintillations, and all the rest using AI or machine learning algorithm. So yeah, I think it's a very good future task, and Dr. Frank might also want to continue looking at this at some point, extend his study through AI detections and also simulations analysis or model identification or no, trying to um, consolidate or complement these studies with other analysis or methods. It's a welcome development. And we have our last questions, which is, I think it has to do with why you are using ROTI at 10 minutes rather than 5 minutes.
Oh yeah, thank you for that question. Yeah, so unfortunately, I didn't really have time to get into the methodology, but this one that you used, it's a ROTI average. So after calculating that 1 minute ROTI, you can average maybe to 5 minutes or 10 minutes, and depending on that ROTI average, uh, it helps you to be able to detect plasma bubbles. Because remember, ROTI is detecting multiple scale irregularities. And so the way that we wanted to do is I was trying to look for an average of ROTI that can have a good correlation with the S4, the scintillation index. So by adjusting that average, or even when you're calculating ROTI, remember you're using a moving window, you can then have a different scale size depending on the window that you're using, or the average that you're using, whether it's 1 minute or 5 minutes or 10 minutes. based on that variation, try to look for so 10 minutes is the one that has got the best correlation with the S4 index. Because remember, I was trying to use ROTI so that it can be a substitute for the S4 index. And so for 10 minutes, that's what we found to be, we have the strongest correlation with the S4 index, so that amplitude variation is almost like maybe 0.8 correlation between the two of them. So that is the reason why I use that 10 minutes.
Yeah, so in essence, you are saying that in the study, we look at all of the possible
yes.
time interval,
Yes.
like 5 minutes, 10
Yes.
minutes, and you found that 10 minutes is best
Yes.
in this situation.
Yes.
All right. Yeah. Thank you very much, everybody. I think we have there's no other question. So there is an email address here. Some of these email address you might want to take note of
Let me
them and
see.
yeah,
All right,
communicate
let me copy.
later with
Okay.
them. And thank you everybody that contributed to this discussion. And this is what we want on this platform. If you can even unmute yourself and put the questions forward, we will appreciate that more, so that we get to know you. And when the time comes and we need to deploy our instrument, you already in our list. So we have already spoken with you, and we know you are not a stranger. And yeah, thank you again, Dr. Frank. Next week or next month, we will have another edition of CONGA, which is the 22nd CONGA meeting series. And I will inform you about our next speaker. But in the meantime, I also want to say that our website, CONGA website, is still under maintenance, and we are updating, trying to change some things, one or two things here and there. So hopefully it will be ready soon than later. So we will probably come up with another link for our website next meeting. So if there is no any other question, is there any other question in the house?
Hello, Dr. Jonah.
Yes, please.
I want to humbly suggest if you have this membership, number of members, names of members, their countries, and all that, maybe as some part of the website.
Okay.
I think that would be a way of collecting data on people that are regular and they are very keen and interested in the project.
Awesome. Yeah. If I get your question clearly, you want us to put the names of the members on the website?
Yes, please.
Oh, okay. And how does that relate to how we know who are attending or who are not attending? Do you want us to do something further than that?
Yeah, I know we have categories of membership,
Yes.
as we have in other bodies.
Yes. We have like 254 right now that I send emails to every day that we have this meeting. And we have more than that.
Of which I'm one of them I receive.
We even have more than that. People that have not registered, but they are attending one way or the other. So, but people that attend are mostly around 30 kind of average that we have that attend the meeting because of the time zones. We don't get a lot of attendance, but we are satisfied with the people that attend, and we will be happy to have more people to attend the program because it's very important. So, like you said, I'm going to put this, I think we had it in the former website, but I'm going to make sure it's visible to us again. I'm protecting people's data as well. I'm just going to put the name, which is public information, and one other thing that is public information. So I may not add the emails because that may be data for, I don't want to put too many information. But for the name, it's a public information, so I'm going to add as much information as I can add. Thank you for
So
that.
what we do at Africa Subcommittee of IAF,
Yeah.
International Astronautical Federation, of which I'm a member.
Mm-hmm.
We publish names of members on the platform.
Okay.
And you can even click and zoom into the person's maybe profile. And to become a member, you submit application and then also CV. So your motivation for joining, and then a CV showing whether you qualify to even be a member.
Yeah, I think we are we are going to get there. That is a high level membership requirement. But for now, we don't really require CV because that is totally high level. Well, I think I understand the part that we need more serious members to join our group. So we're going to look into that a lot. And I'm going to be like taking attendance to identify people that are constant with us, right?
That will also be great.
Mm-hmm. So that will help us a lot. And please feel free to sham in when you want to sham in, like just Dr. Francis is doing. It's very helpful so that we have a very good meeting discussion every time we are here. And I think Dr. Bastru is saying something. Okay, good. Yeah. Yeah, we are very careful about that. We have this information and those information that are personal, we don't want to put it, but names are public information. We have these names on LinkedIn, so it's a public domain. It's, it's not nothing special. Universities also maybe nothing special, but we will see what information we can provide out there. And we will see a sample, just like Dr. Francis is saying, we will see a sample of other websites, what they are doing, so that we don't put too much. And that will be helpful for us. Thank you again, Dr. Francis. Thank you so much.
Thank you, Prof.
Yeah. All right, so we'll call it a day here. Thank you all for this wonderful edition of CONGA 21st edition. We are grateful again for your attendance, and we look forward to seeing you again next month series. Thank you. And stay safe. You are in the US. We have a lot of storm here going on, snowstorm. So thank you all.
Thank you. Bye.
Bye-bye.
Thank you, everyone.
Mm-hmm.
Thank you, Dr. Jonah.
Yeah, thank you, Frank. Yeah, that was
Yeah, stay
wonderful
safe there in the
presentation.
cold. Yeah,
Bye-bye.
thank you.
Thank you.